So in the last video, I derived the Euler-Lagrange equation for an integral of a function of y prime, and x. But now I'm going to derive the Euler-Lagrange equation, the more general version, for an integral from x1 to x2 of a function of y prime, y double prime, y triple prime, etc., and x. So it's going to be a more general equation. Alright, so the goal was to find the function that optimizes to the functional j of y, subject to the constraints in yellow. So if you haven't seen my previous video on this, it's called Introduction to Calculus of Variations. Maybe I'll change the title, I'm not sure. But in that video, I'll give you the intuition about like thinking of the input to functionals as an infinite dimensional vector-like structure that is a function. And the output is just a scalar. So we're going to be optimizing j of y, given in this red box, in which we have y, the first derivative of y with respect to x, all the way to the nth derivative of y with respect to x and x dx, from constant x1 to constant x2. As for these constraints, we're saying that the 0th derivative of y of x1 is equal to some constant, that is, y is equal to a constant at x1, then y of x2 is equal to a constant, and y prime of x1 is equal to a constant, y prime of x2 is equal to a constant, all the way to y, all the way to the n minus 1th derivative at x1 is equal to k constant n1, and y n minus 1, the n minus 1th derivative of y with respect to x at x2 is equal to a constant as well. So why don't we include why don't we include the nth derivative of y with respect to x in these constraints? Well, it's because we don't need them. And the reason why it comes down to the way that we do the integration by parts to derive this. So therefore you don't really need the nth derivative of y to be constrained. So just like before, we introduced the perturbation, and the reason why we do this is because we want the derivative in all directions in the domain to be equal to 0, just like in last video. This perturbation is equal to y sub epsilon is equal to y plus epsilon eta, just as last time, but except for this time, since we have more boundary conditions, and because of these boundary conditions, the nth derivative of eta with respect to x at x1 is equal to the nth derivative of eta, sorry, not the nth derivative, the jth derivative of eta with respect to x2, which is equal to 0, where j is 0, 1, all the way to n minus 1. N minus 1, yeah. So the reason why this is true is because remember that we want to remain inside the hyperplane, because your domain is actually restricted by these boundary conditions. So the amounts of dimensions that you have is n minus the number of boundary conditions, where n is infinity, because you have an infinite dimensional vector, which is a function. So that means that you can only move in directions in the hyperplane in your domain. So that's why eta must be equal to 0. It's because eta at those points and the domain must be equal to 0, because otherwise you'd be going in directions that are perpendicular to the hyperplane. Alright, so let us begin simplifying. The first step is to use the multivariable chain rule to expand this stuff in here. And we do it by taking each and every possible path to epsilon and adding them together. And then we also take the path from L to epsilon through X as well. Yeah. So we take all possible paths. All right, so then the second step is to recognize that the partial derivative of x with respect to epsilon is equal to 0. So this term over here is 0, so we can just get rid of that because x does not depend on epsilon. So yeah. And the third step is to recognize that the partial derivative of the partial derivative of the jth derivative of y sub epsilon with respect to x with respect to epsilon is equal to the jth derivative of eta with respect to x. And that is because you have this equation over here. If you take the derivatives on both sides, then you get you're left with the etas right there. So we turn these terms into etas, eta primes, and eta nth derivatives of etas with respect to x. So now if we evaluate at epsilon is 0, then we can distribute this evaluation to each and every quantity of partial derivatives in the terms. And we can say, for example, that the partial derivative of L with respect to y sub with respect to the first derivative with respect to x, so y sub epsilon, evaluated at epsilon is 0, you can use this equation to say that's equivalent to evaluating the y prime sub epsilon at y prime. And that's the same as taking the partial derivative of L with respect to y, because it automatically makes that substitution for you when you take it directly with respect to y. Now let's distribute this integral to each and every term. So let's take a look at the mth term in this summation. Now let's integrate this mth term in the summation by parts. Well, for the first integration by parts, you get this. And in red, I've outlined an expandable term at the end. So you can actually expand this term again. And eventually, if you keep on doing this, then you'll get to this eta term on the end. And the reason why you want that eta term on the end is because in the end of doing all this, you want to apply the fundamental lemma of the calculus of variations to simplify everything. And also, these terms vanish. That's why, these terms vanish. That's why you can even apply the calculus of variations lemma. But in terms of integration, in terms of integrating by parts, you can imagine that after each and every expansion, you get this kind of term at the end. You're adding on this kind of term. And then at the end, you get an expandable term. So it's kind of like generating these terms with this thing on the end. Now, because of these boundary conditions, which would set the jth derivative with respect to x of the y's equal to constants evaluated at the x1s and x2s in the domain, is because, this leads to this condition on the etas, this restriction on the etas, because you want to stay in the hyperplane, as we mentioned before, in which your j's range from 0 to n minus 1. And the reason why we chose the boundary conditions to range from the 0th derivative all the way to the n minus 1th derivative is because of this term right over here. It's because if you imagine, if you vary k is equal to 1 to m, where m can be anywhere from 1 to n, that means that all the possible values of eta, the m minus kth derivative with respect to x of eta, falls within the range of so all those possible values. Sorry, I'm getting tired. It's already like 2:47 in the morning. Wow, that's late. And I'm making this video. Please bear with me as I get back on track because I'm tired. Right, so if you imagine this m minus k is actually the j right there, then like if your m reaches n, then you'll have then your maximum possible eta would be n minus 1 when k is 1, and that means that you don't need an nth derivative boundary condition because like this won't reach any of the ends, and it vanishes. We want to vanish, so that's all the boundary conditions we need. And because this vanishes to 0, because it vanishes to 0 because we, oh my gosh, I'm so tired. It vanishes to 0 because I don't feel like restarting this video, but yeah, I'll just keep this in the video. So it vanishes to 0 because it vanishes to 0 because, oh yeah, eta at x2, because of this condition. And you're evaluating the x1 and x2. Okay, got it. And then you're left with this term on the end, which is equal to that. Sorry, that took me such a long time because my brain was slowing down because it's getting late. So for each and every term, if we substitute the mth, if we substitute our expanded version of these terms into the equation over here for 0, then we get this summation term plus this term over here. This term does not apply to our mth terms thing because it's actually the 0th term. And the mth terms thing that we did starts at 1. Yeah. So now what we're going to do is that we're going to factor out the integrals. So that means that we're going to like make it the integral of everything. We're also going to factor out the etas over here. And we get this. We get all this stuff is equal to 0. And now we can apply the fundamental lemma of the calculus of variations. So if we apply the fundamental lemma of the calculus of variations, then it must be true that the term in these parentheses is equal to 0. And this is only because eta vanishes at these boundaries. That's why we can apply the fundamental lemma of the calculus of variations, which can be proved, but I'm not going to prove it in this video. Alright, so we have derived the more general Euler-Lagrange equation. So yeah, this is the equation in green, and the critical points that you have are all y such that it satisfies this Euler-Lagrange equation in which the y's satisfy the boundary conditions displayed here in the yellow box. And that is, if you want to optimize this equation, these critical points may or may not be y-hats. You'll have to perform some kind of like second derivative test or something like that. Maybe like an analog for higher dimensional space. Or wait, actually, you could just apply the second derivative. Oh, wow, yeah. Yeah, you could apply the second derivative test on it because this is only a function of x. Oh, whoopsie. I made the same mistake in the last video, but it's a small mistake. I just said that you have to like apply the multivariable version of the second derivative test when you could just do the single variable version. You know, just to like test if it's a local maximum or minimum. And yeah, that's like the end of the video. It's 2:57 in the morning. I just decided to stay up extra late because I want to finish this video by today. Why? Because I don't know. I just wanted to finish it. Alright, so that's the end of this video. It's 2:57 in the morning, almost 2:58. Yep, 2:58. Yeah, so my research rotation for my PhD, that's going pretty well. I have a timeline now, which is good. I have this really cool idea too. And it's the same idea that I presented, I believe the video is called, it's in one of my videos. It was 2 videos ago that I presented it. It was basically machine learning regression, but with error bars. And the idea I had was that, what if you can, if you assumed that your errors vary as a function of x, but in reality, your errors are constants, then what if you can kind of tweak the model so that it's what if you can kind of optimize it such that the errors converge to constant errors? Like, that'd be pretty cool if you could do that. Now that's a theoretical thing. I'm working on more applied stuff right now. But that'd be cool. And also, You could, if we could do large language models, if we can incorporate that into the project, that'll be pretty cool. We can mine the literature for hotspots, maybe. Hotspots and enzymes, amino acid sequence. That'll be pretty cool. Alright, I'm just kind of blabbering on about stuff, but see you in the next video.